homology for quite a long time, and I'm working with virtual knots. And well, actually, I wrote some books on that topic. And so it's really important for many of us to listen to today's talk by Scott Baldridge, who is going to compare, and it's often a very important when we have two different parts of mathematics. So we're going to compare a new theory of new homology theory with homology with Khovanov homology version. So let's welcome.
So, first of all, thank you so much for inviting me. I really appreciate it. And that's what we're going to talk about today. And this is kind of, when I think about this is, this is a kind of an exciting new area that virtual links can be applied in. So one of the ways to think about it is if you took just a set of classical knots and said, well, what can we do with them, thinking of them as trivalent graphs, you wouldn't capture, you would not capture all possible trivalent graphs. In other words, you need to enlarge your notion of classical knot to virtual links in order to actually get all the different trivalent graphs that we're studying here. So it's one of those beautiful situations where it's motivating why virtual links are so important, and it's giving a direct link to another kind of completely different subject. And we'll talk about some of it, or it feels different. Now it's going to be quite similar. This is joint work with Lou Kauffman and Will Rushworth for this archive article, but really Ben McCarty's been part of the whole thing as well, so it's important to put him in that list as well. And today we're going to, well, let's just do some preliminaries. So it takes a couple of boards just to get to the goals for today. But I want to kind of recap what happened in Lou's talk last week and my talk on Thursday. And so we'll just do this very quickly just to remind everybody of the terminology and all of that. So Lou talked about the Penrose formula. So if you're given a ribbon graph in particular, most of the time we just show planar graphs because those are kind of the easiest to deal with. And for Penrose's formula, it works really well on a planar graph. If you pick a perfect matching, and he talked about perfect matching, and I talked about perfect matchings. That's just picking edges so that every vertex is paired with another vertex. So if you go around the graph, you can pick perfect matchings, and then you can pick a set of perfect matching edges, and that is called the perfect matching. So if you decompose your graph into circles via this inductive process, right? You imagine that you go through every perfect matching and replace it with either an open or a cross. And whenever you see a circle, you replace it by Q inverse plus 1 plus Q. You'll get a polynomial. That's called the Penrose formula. And what it does is if you plug in Q equal to 1 into that polynomial, you will get the number of 3-edge colorings of G. So this is kind of, it seems far removed from knot theory at this point. It seems to be it's a beautiful result that comes from Penrose from 1971, but even that goes back to 1956 because he sat on it for a few years. He was studying tensors using these pictures. And it's a beautiful result that, you know, in some regards is going after what's the 4-color theorem, because if you have a 3-edge coloring of a planar graph, then you automatically have a 4-face coloring, which goes back to, you know, all the way back to Guthrie and his discussions of the fact that he can paint the colors of the counties in England with only 4 colors, so that no 2 edges of the counties have the same There's no two counties that are adjacent that have the same color. So that part is something that Lou gave a beautiful presentation on last week, showed you how to get those colorings. I'm upgrading this to a polynomial. He was just literally just working with this minus, where you just plugged in q equal to 1. But you can upgrade it to a polynomial if you make it dependent upon your perfect matching. So for every perfect matching, you'll get a different Penrose formula, different Penrose polynomial. But if you plug one into any one of those for any one perfect matching, you'll get the same number of 3-edge colorings, because that's an invariant of the graph itself. Once you're counting the total number of 3-edge colorings, it doesn't really matter. So 2 years ago, I put together, and this was the talk on Wednesday. So this is a summary of Lou's. On Thursday, I talked about the 2-factor polynomial, which is a slight modification. It seems like a slight modification of the Penrose. It's got the same first, it's got the exact same first equation, but the second one looks a lot more like what you might see for the Jones polynomial. And so instead of replacing each circle or immersed circle with q inverse plus 1 plus q, we're just doing q inverse plus q. Now, when you plug 1 into that, it also counts in interesting, important information about a graph. So let's look at that. It computes interesting information. And
oh, excuse me, and so the first polynomial, so it's q inverse plus 1 plus q. It looks like something like Kuperberg's polynomial. Well, it's strange. So the first skein relation looks like that for Jones, and the second looks like that for Kuperberg.
Right. Yeah. It's there's something there. So wherever you have a question is probably an open question.
Yeah, excuse me. So may I see two variables in the second formula? So in the first formula, you had q only.
Right. Oh, so the interesting thing about what I proved in 2018 is that, and I'll talk about this later in terms of the flip moves. You can put an A here and a B here and any C.
Okay.
And it can be multivariable if you like, whatever. And that will be an invariant of the graph. But it may not be invariant of the corresponding knot that you'll see in a minute. But you know, any polynomial that's generated in this way that is an invariant of a knot will automatically be an invariant of the graph, or excuse me. Yeah, you can usually port that over to being an invariant of the knot of the graph. What's neat is that you should be able to, you know, there's lots of interesting things that are going to start to happen where you might see potentially new invariants of virtual links by considering the trivalent graphs. Okay. So the interesting thing about the 2-factor polynomial is that if you plug 1 into it, and you take now for a planar, this will always be non-negative. But if it's a ribbon graph, non-planar ribbon graph, then it's potential that this could be a negative number. But if no matter what, if you take the absolute value of it, it counts the number of 3-edge colorings where the perfect matching edge, the edges of M, these guys, are all share the same color. So, you know, if in Lou's talk, he had red, blue, and purple, purple being kind of where the the formations overlapped. And so you could take in Lou's talk, every time that he had a formation, you know, one of these things. Every time they overlap, that would be a purple. That would be a perfect matching. So so this two-factor, it doesn't count all the three-edge colorings, but it counts a subset of the three-edge colorings that basically have the same coloring on the perfect matching. And if G is same thing as over here, as in Penrose, if G is a planar graph and there exists an M in the perfect matching, a particular perfect matching such that this is non-zero, then it's three-edge colorable, then it's got a four-face coloring. So one way to prove the four coloring theorem is to show that there exists perfect matchings with this condition. At this point, yeah. So then the other thing that I talked about on Thursday, and we'll just briefly to catch people up, there is a relationship, and Luke mentioned it as well, there is a relationship between the two-factor polynomial and the Kauffman bracket. And the way you see this is you take a perfect matching edge like this. It's got a virtual crossing in it. And if you apply the two-factor polynomial, i.e. one of these, what you see is that you can unwind this virtual crossing and it gives you an open, a zero smoothing. And if you can unwind this using a virtual moves and you get a zero smoothing and a one smoothing. So
by the way, excuse me, are your invariants mutation invariant? Is there any chance to get a mutation, something which detects mutation?
Way to think ahead. So just let me go.
Well, I think for virtuals, it should be quite easy because for virtuals, there should be picture value things, and well, picture when it mutates, it gives another picture. But for classicals,
no, it's the other way around because you know, if you're doing a oh, Lou's here. It's the other way around because there's no real meaning to virtual mutation. Right? They think of it as classical. Classical mutation is you take a ball in S3 where the knot intersects it in 4 places. And then you do a diffeomorphism of that ball that gives you the 4 different. But in this case, there's no, you're not, if you're going to think of a virtual knot, it's sitting inside a sigma G cross I. So there is no, I don't know what you mean by taking out a piece of a virtual link and turning it around and putting it back in.
Well, I mean just the graph when we take into account classical crossings. So we have a graph and we take it away and rotate and insert. So if the graph is not planar, so
I'm going to get there. I'm going to get there. So let me, I'll answer your question as we go along. Okay?
Fine.
But it's a good question. It's an excellent question. In fact, it does have something to do with it. All right. So, so the brief answer is there is something there. I will get there though soon. Okay. So, I guess I need to go back here. So, we saw that this was basically equivalent to that. A regular classical crossing looks like that. So, if you replace it the other way, you say that these two things are identified. Now, if you work out what that looks like for going. So we take our map K going from the graphs to the virtual links. And if you switch this around, you see that this is the map that takes you from a perfect matching edge to a virtual crossing, or crossing followed by a virtual crossing. And if you do that, then if D is a matched diagram, i.e. one of something that's made out of things that look like this, of your graph with your perfect matching, then K of it, it's a virtual link diagram. And of course, as I just showed you down here, D of Q is identically the Kauffman bracket of Q. Now,
by the way, have you had a chance to think whether you can get my parity bracket for that?
yes. Yeah. So so let me go a little bit further, but the idea here is anything that you can define for a virtual link can then be defined for what we'll call this thing in the near future a graphene, and vice versa. Okay. So the Penrose, the final point is that the two-factor bracket is naturally the thing that you would consider over in the virtual link world, because it's the thing that comes with, it's the thing that comes, it essentially becomes the Jones polynomial. But if you're trying to do it with Penrose, Penrose is not a virtual link invariant. It remains a graph invariant. It satisfies being invariant under the flip moves. But as a virtual, and you can certainly port it over and calculate it, but it'll change depending on the Reidemeister moves. All right. So 2 years ago, part of developing the two-factor polynomial, I was able to categorify the two-factor polynomial and get a homology theory that looks, as you might imagine, strikingly similar to Khovanov homology. So it behaves in exactly the same way. You create a zero smoothing and a one smoothing, but the one smoothing now is with a virtual crossing, and you have to know how to normalize it. So if you put an orientation on your graph, take your graph, take away the perfect matching edges, then you'll get a set of loops, and then you have to orient all those loops. So if you give an orientation to two cycle components, take away the perfect matching edges, then you can define a crossing or a perfect matching edge as a positive crossing, and a perfect matching edge that looks like this as a negative crossing. And so then you can compute an n plus and an n minus. If you now fill in the whole procedure of building a hypercubus states and assigning vector spaces to each of the states and maps between them, the vector spaces that you choose are going to be, oops, I'm going to do this. The vector spaces you're going to choose have Z2 coefficients. That's important. And then mod x squared, with the degree of 1 being 1 and the degree of x being -1. All should look familiar to Khovanov. People have studied Khovanov homology. And then you have the diagram, and you normalize by this, the number of plus crossings, in quotes, and minus crossings in this form. So let's see an example real quickly for those of you that may not study this every day. So what I'm going to do, and so this one's a non-planar graph. It's got a virtual crossing right here. And if I put an orientation on it, I see that this is a plus crossing. They're going in opposite directions. But here, that's going to be a minus crossing. If it's planar, you can set it up so that they're all plus crossings. There's a way to compute them so that they're all plus crossings.
So it doesn't mean the source sink orientation? A plus?
No, don't need it.
Okay.
We're not doing integral.
Okay.
So you can just.
But plus means that there is this local sourcing. I mean, and minus means that there is the opposite one.
Yeah. You can translate all. You certainly can translate all this into different choices on the source sinks.
Right.
Okay. So if I'm making the hypercubist states or the diagrams, here's the 200 resolution because I've done two opens at the two perfect matches, and then if I do should be the 10 and 01.
Well, is there any chance to get a magnification of what you're showing?
There's a fit. Oh, there
okay,
you go.
okay, fine. No, fine.
How'd you do that? That's interesting. That's good. So you just go through and just like in knot theory, you do all open, and you start going through and sprinkling in one smoothings, and the final one is 2 1 smoothings. So I'm looking here, these as being the parts that are the smoothings, and it's not really a smoothing. That's why it's in quotes. It's more of an immersion. And if I look at this, I see that I get all the same exact types of maps as before. I've got one circle here, and it goes to 2 circles. So this is going to be what's usually noted as a delta map. For those of you that are maybe a little new to this subject, delta of 1 be 1 tensor x plus x tensor 1, and delta of x tensor x. So what we do is we replace this with v. Over here, I don't know, it's kind of off. Replace it with v and the vector space v. And here we do v tensor v. Like this. V goes to v tensor v. And so this delta map would look something like this. And the same thing's happening here. You're going from 1 to 2 circles, so that would also be a delta map. But then over here, on this final one, we see that there's only 1 circle. And so we're taking 2 circles to 1 circle. That would be a multiplication map. And multiplication is just multiplication in the in the algebra that we've created with V. So that would take, for example, 1 tensor x to x and x tensor x to 0. Now, because this is a virtual link, you also have the possibility of going from 1 circle to 1 circle, and that would be the eta map. So with that all being said, then you can actually write down the chain groups. So this would correspond to just a V, and it would only have, and it's normalized, or it's, excuse me, it's a graded group via the degree right here. The degree right here. So degree. Did I do something wrong? Yeah, I did. That's okay. Everything here is shifted down by 1. There. That's better. So this gives you the gradings for this V, and then I have a V tensor V here, and it will be graded in it'll be a 1 tensor 1, which I'm just writing as 1, 1, and 1 tensor x and x tensor 1, and there'll be 2 copies of it. It'll be v tensor v plus v tensor v. And you can then write down the groups. Of course, back here we'll have just a v again, but it's shifted up by it's shifted up to the 2 and the 1, 0 spot. And then the maps. Well, the maps. So there's your delta map, taking x to x tensor x, and 1 goes to, in this case, I got it set up. 1 goes to 1 tensor x plus x tensor 1, but it's going to do it for both of them. And then we have these 3 left over, and then there's nothing hitting the 1, 1 or 1, 1, comma 1, 1. And then for here, these are multiplication maps. And I see that 1 tensor 1 gets mapped to, comma 0 gets mapped to 1. But 1 tensor 1, comma 1 tensor 1 gets mapped to 1 plus 1, but we're in Z2 coefficient, so it's 0. So this goes to 0, and that's a cohomology, or a homology element. And the same thing happens here. I can use any one of these 3. This x tensor 1 will get mapped to x, and these will be homology, can be used to be made into homology elements. And then oh, this map has got to go to x tensor x and x tensor x. And there's one extra generator left over. And so what I see is that my homology, there's nothing in the -1, and there's nothing in the 1, but in dimensions in 0, I have Z2. Yeah. In 0, I've got Z2 plus Z2. And in -2, I've got negative Z2. All right. But that's exactly if you look at that carefully enough, that is, well, the graded Euler characteristic of this is the 2-factor polynomial for that. And if you check, for example, the 2-factor polynomial of this would be q minus 2 plus 2 plus q squared. And so that corresponds directly to taking the ranks in the different gradings for this guy. Okay, so if you're looking at this a little bit carefully, you see that this right here is exactly the Jones polynomial for the unlink with 2 components. It's just basically q minus 1 plus q to the minus 1 plus q squared. And so, and then when you compute the homology, you see that you're also getting the homology of the Khovanov homology of basically 2 unlinks with an unlink of 2 components. And so you suspect that maybe this right here, there's a move on this that should make it the same as this. Basically 2 ungraphs on the components. All right. Over here. That's how you compute the homology theory, and it's, of course, it's the fact that it looks like Khovanov homology shouldn't surprise you at all. So let's keep going. Notice that the 2-factor polynomial can be 0 when you evaluate it at 1. So that would be, for example, a situation where you have what's called a bridge. But you can also get it in non-bridge examples. So if you were to compute the two-factor polynomial for that graph with that perfect matching, and plug in 1, you'd get that it was 0. But the two-factor polynomial itself wouldn't be 0. In other words, there's more information in the two-factor polynomial than just in the number that you get when you evaluate it. And the same thing can be said about the homology theory. The homology theory is going to have, we can show that it has actually a lot more information in it than simply the polynomial, the two-factor polynomial, which it's its Euler characteristic. That shouldn't be too surprising, but the point being is that even in the case where your graph has a 0, is not really telling you anything about the number of colorings that have this same color on the perfect matching edges, it's still providing a lot of information about the graph. And that it's my hope to exploit that information as we go on, as we learn more about these homology theories. Now, this is going after your question. So the invariants are all invariant in graph theory under flip moves or two isomorphisms. So a 0 flip move is just you take part of the graph and you flip it, a component of the graph, and you flip it over. And so you can see that there's nothing to check there. This is a little bit more interesting. This is where you've got a part of the graph that's connected by just a single edge to something that you can put a circle, or that lives in a disk. And you can flip that over, and that all these polynomials and invariants are invariant under that. That's also pretty easy to prove. But when you get to here, the two flip move is where all the pain comes in. So, for example, it's not, you might say, well, could I build a homology theory by categorifying the Penrose polynomial back there? And that's what I actually tried to do for a long time, was to come up with a categorification of the Penrose polynomial that was invariant.
I think we should contact Belo Bolobash. Bolobash, he has very broad interests, and he gave a talk here in Moscow about lots of things, and in particular graphs. So I think it would be nice if you contact him and give him such a talk.
Oh, I'd love to do that. Yeah, it's like I said in my Thursday talk, there's a surprising number of mathematicians and actual theoretical physicists that were interested in the four-color theorem from from a physics standpoint even. So so for example, there's a lovely little article on the archive with S.T. Yao as one of the co-authors. So even Yao.
As for Yao, we have this Moscow-Beijing seminar. Well, it's the time is bad for those who live in the U.S., but actually he often comes to that seminar. So in this semester, everything is occupied, but starting from February, we can try to find some time. And he comes very often. Yeah.
I like Yao a lot.
Yeah, it would be great.
His interests are diverse and amazing.
Yeah, sure.
And but he has a very specific physics reason why he's studying these graph problems. So and I won't go much into that here, but it's not unjustified why theoretical physicists are interested in these problems. So so for today, the goal for today, describe issues with defining graphenes. So what I'm going to do is I'm going to build a new category of trivalent graphs with perfect ribbon graphs with perfect matchings, and the K-map here is the same K-map as before. That gives us a functor from this category to the category of virtual links, and it's an isomorphism. And that means, that means that whatever invariant you're happy to define here, it automatically lives as an invariant there. And vice versa. If you have an invariant of graphenes, you immediately have an invariant of virtual links. So it gives you a way of really starting to look at links in completely different ways. There's all sorts of things that graph theorists do with graphs, and this is in some sense opens up the possibility of finding new invariants.
I can also recommend you some mathematician topologists in Moscow who are related to Manchester, and Manchester claims that it's the motherland of graphenes. So topologists in Moscow who are related to chemists and who are related to theory of graphenes, Fullerands and other things.
So we're being a little. So graphenes are this beautiful object, right? You know, they're C bonds with double bonds. You know, this type of thing. And these actually, with the double bonds, they actually look like perfect matching. So that's really the end of where we took advantage of the word because it gives you the same sort of picture in for us. But the thing that you said, you know, a lot of graph theory comes about from studying circuitry and so on. So there's a lot of interesting types of things that you can do with graphs that you may not have ever thought to do with knots. And then the second part of the talk today is if I have a graphene, I can define, because I got this isomorphism, I can literally just define the Khovanov homology of it by first mapping my graphene into my virtual links and then just computing the Khovanov homology of the virtual link. Of course, this is with Z2 coefficients. You could do it with Z coefficients as well, but for our talk today, it'll be Z2 coefficients. And then you can compare this to the homology theory I just described. And but first, so that's the kind of the plan for the rest of the day. First, let's talk about the issues with trying to define a graphene, because there are some. So let me grab a. So the first one is this. See, we have two choices. Right? If I have a perfect matching edge, there's no way for me to tell whether this is up or that is down. So, you know, or this is up or this is up. If this is up, then this would be the thing. But if I'm looking at it upside down, I would write that down. So there's some choice. There's some there's a symmetry here that doesn't exist here. So we have to break that symmetry. And the way that we do that in the book or in the paper, so we choose a side. Now, so we use a dot to choose the two different sides. So this would be that. Now, it doesn't. If you look at this, so that breaks the symmetry and allows you to distinguish between which of these two is the correct map. We could have chosen an arrow, right? Like if you choose an arrow, you'd be able to determine which one to choose. But because graphs use arrows all over the place for different types of, there's source sink type arrows on graphs. There's flows on graphs. There's all sorts of things where you use arrows on a graph. We chose a different notation just to keep the things separate. So, but you have to choose a side. Once you choose a side, then this is what we call a directed perfect matching. A directed perfect matching edge. Notice that that this is a Z move. So if you want to consider virtual links up to Z moves, then you can drop the dot. And so that's why all throughout we've been, like you've seen me, I've never put the dot on, because the things that we've been talking about are invariant under Z moves. The Khovanov homology is invariant under Z moves. So there was no real point to putting a direction on it. But if you start to talk about fundamental group or any other type of invariant that does rely upon, that is not an invariant under Z move, then you need some notation to describe that. All right. So this is okay for. So if it's undirected, then we just do this, and this is okay for Khovanov. But not for pi 1. So if you want to do something with pi 1, then you're out of luck. Okay, there's another issue, which is we choose you can get the theory to work for either one of these choices. You could have chosen, this is of course K of that, but instead of having it go the under strand going, the bottom strand going over, I could make the bottom strand go under, and I could create the same theory. Same theory, as long as I made that consistent. So it would be nice to somehow capture a theory, perfect matching edge that allows you to go to have the the bottom strand go under instead of over. And for that, we chose basically a sine graph. Oops, I'm gonna get the. So in this way, it's the other way around. But a sine graph is where you use a dotted edge. And it usually means, in graph theory, it means a negative edge. There's so many positives and negatives and parities that they're floating all around here. Don't get too concerned about it. Just realize that you can do a negative edge, and then you can capture this type of crossing, if you will. And it all goes through nicely. So this is a sine graph. Now, you may say, Scott, I don't need a sine. I could just work with all trivalent graph with all positive edges. And the answer is, yeah, you can. This allows us to get after something I want to talk about in just a moment. So the other issue that comes up is the virtual moves. Excuse me. Graphene moves. No, the virtual Reidemeister moves suggest the following. Let's see. So if I have a perfect matching edge, but it has a twist in it up above, then by the K-map, I get that, and I can then pull this down. This is equivalent the virtual Reidemeister moves, or that, and then that's equivalent to something that looks like this. I won't go through it, but that's one of the things that you can work out for yourself. And then by the K-map again, this is actually equal to that.
Roger Fan is with us now.
Huh?
Roger Fan is with us now.
Oh, nice. So the point being is that since the virtual moves allow you to do this from here to here, that induces a new move that you would put on a graph, which basically says that if I have a twist at the top of a perfect matching edge, I can transfer it to a perfect edge a twist at the bottom of the perfect matching edge. So this is what we'll call a G4 move. In just a second. And just for just note that this is actually a negative edge. So you can convert between negative edges and positive edges at the cost of introducing a twist. So that's what I meant when I said before that I could get away with never having a negative edge, but they're still valuable in terms of what we're trying to do with the graphs, the ribbon graphs. Okay, so that means that for the graphene moves, what we're basically going to do is just everything that you see in a virtual Reidemeister world, or virtual links, you're just going to imitate on a graph. So a G1 move is exactly the same thing as a Reidemeister 1 move. And there's a couple different variations on this, but that's basically it. You can, if you have a perfect matching edge between a piece of the arc, and you can just remove it. Similarly, this looks like a Reidemeister 2 move, and that's exactly right. You can replace it with that. And that, by the way, is the thing that proves that back here, when we did this example back here, this guy is just a Reidemeister 2 move to the two unloops. So that's why those things are why that had the same homology theory. And then of course here, this is just a Reidemeister 3 move. Just have to make sure that one goes over. This one goes over. And so there's your Reidemeister 3. We had a new move here, the G4 move that I just talked about, which allows you to take twists from above and move them down. And then the G5 move, which I also just talked about, which is I can replace a negative edge by a positive edge. Okay, so if I have these moves on a trivalent ribbon graph, and I add in the virtual moves, all the regular virtual moves that you know and love, then I get what are called graphenes. So graphenes are match diagrams that look like this, module the equivalence relations of G1 through G5 in the virtual moves, and then you can then upgrade K to a functor between the two categories, the category of the graphenes and the category of the virtual links. And it's an isomorphism on the level of categories. So that means that this, and you can now see that these really should be isomorphic. They basically have the same equivalence relations. And so therefore, if you have an invariant here, you have an invariant here and vice versa. So that's really that's how you build the graphenes. And you see that you have to be a little bit careful due to all the things that happen with ribbon graphs. And so I want to talk about that next. Let me plug my computer back in so it has some power. Okay. So graphenes describe all oriented surfaces associated to a abstract graph. What do I mean by that? So here you want to go, you want to be able to go all the way down to, so we're not really in knot theory or topology. We're thinking about just abstract graphs. So let me give you an example. If I have this graph, which is just the old theta graph, I see that it's got, I could think of this as a graph embedded in a surface, and I could ask, well, what's the smallest surface it's embedded in? And it's clearly a sphere because it's planar. You can capture that by seeing that there are 2 vertices, 3 edges, and 1, 2, and 3 disks that you glue in. And so the Euler characteristic will give you that that's a sphere. But that's not the only ribbon graph that you can have. By a G4 move, you can think of this graph. And this graph is this is a different ribbon graph in some sense, but if you count it up, it too is a 2-sphere. You can see that because the disks that you're going to glue in look like this. You've got 2 vertices, 3 edges again. There's 1 disk that you glue in here, 2 disks here, and 3 disks there. So when you glue in the 3 disks, it's a different form of a sphere, but it's also a sphere. The other thing you can do is a G5 move, which gets rid of one of these twists at the cost of turning it into a negative edge. Now, if I check what type of ribbon surface that's associated to it, I see that I got 3 edges and 2 vertices, same, but now I've got only 1 disk that I'm gluing in. So the Euler class on that tells me that that's a torus. And I can do one more G4 move with G5. And that's also a torus, just by symmetry. So the point is that once you have an abstract graph, your favorite abstract graph, if you start putting twists in at each of the vertices, if you have n vertices, you'll have 2 to the n number of ribbon graphs that it can generate. And the point being is that what we did with the graphenes is that each graphene will capture for the given underlying abstract graph. You can modify the graphene in lots of different ways, and they'll to give every single ribbon graph that you can generate off of that abstract graph. So and so that's the power of those, of why we went through all those issues back there. At the time, it's like, well, why are you doing this? But there's a really valuable reason for doing that. And the reason why, let's talk about that for a second. So why is this important? Well, the 2 biggest theorems or the 2 biggest conjectures right now in graph theory is the strong embedding conjecture, and 2, the double cyclic conjecture. And I don't want to get into too much of what they are, but if you were to ask I think if you were to ask any of the top graph theorists, they'd say, yeah, I would love for us to solve the strong embedding conjecture. The strong embedding conjecture says that given any graph, there's a surface in which there's an orientable, these are all orientable surfaces. There's an orientable surface in which it embeds into. So in such a way that the disks never touch each other. So I'll give you an example of that. Here we had excuse me, the disk doesn't butt up against itself along a single edge. So that's what's happening here. You can see that this disk right here is on this side and both sides of that edge. So that would not be a strong embedding. So the question that the graph theorists want to do is say, give me any graph possible, and I can find basically a ribbon graph in which it embeds into a surface of some genus, so that there's no place where the disks, each disk that you're gluing in touches the same edge twice, or runs along the same edge twice. So that's a huge conjecture in graph theory, and the graphenes are specifically designed to capture all possible ribbon graphs. So you have a comment?
Yeah. So I think that we should analyze this question from the point of view of atoms. And actually, atom doesn't change under the virtualization, but the surface. So atom is derived surface, but the other surface does change.
It's a conjecture.
Well,
So the thing that I think is whether you can prove it or disprove it right now, there's not really, in graph theory, there isn't really any technology that I can see that, besides the same old technology that the technology that they've been using for years and years. It's kind of these types of questions are begging for some new invariants, some new technology that will help us determine them. And the really pretty thing that happens with the strong embedding theorem and the double cyclic conjecture is that it turns out that the states, remember the states that I did over here?
So what's the conjecture about?
The double cyclic conjecture is the same thing, that there's an embedding, but the embedding can be non-orientable.
okay.
So the strong embedding theorem implies the double cyclic conjecture. But the states that you create, in some circumstances, actually give you strong embeddings, or they give you double cyclic covers. Double cyclic cover conjecture, I should really say that. So embedded in Khovanov, in this homology theory that I'm describing to you today, embedded in it is interesting relationships to the double cyclic cover conjecture and the strong embedding conjecture. And maybe that can, it's one of the hopes, right? That you have this new technology that can start to make some comments about these really hard conjectures. In particular, are they even true? So in particular, the Lie homology type theory, actually, when you have a non-trivial Lie homology of your graph, so because remember, anything that you define for a virtual link, you can define for trivalent, for a graphene. The Lie homology actually tells you information about about the existence of some of these double covers. And maybe I haven't talked to Will, but maybe that's what Will will talk about next week. So there's a or things that are related, the double Khovanov homology, which will help understand those types of issues. Okay, so there's an advertisement for Will if he's going to talk next week. What time do I have? Time is it? You mind if I go a little bit further, or?
Okay, go on, please. So we are happy to listen to you.
So let's just finish up then. So the last step the goal 2 was to see our KH of the graphene equal to the Baldridge, and I'm only using this to tell the difference, the Baldridge theory, S theories. And the answer is clearly no. The graphene structure, the graph structure, the trivalent graph structure is being modified by the flip moves, whereas the graphene structure is being modified by things that look like Reidemeister. So the example that we did earlier, or an example that's like the one we did earlier, this is equivalent to 2 unknots. And that's this allows for these two things, these two objects to be equivalent where they're not equivalent over here. So that's clearly not the case. But maybe however, the flip moves are contained in G1 through G5. In other words, maybe the flip moves are part of, they're just, it's like classic Euclid problem. Does the parallel axiom, can it be derived from the first 4 axioms? And the answer to that is also no. So again, no. They're a little bit, it's a little bit more special than that. So let's take a look at an example. Move this up here. Basically does it. So here's the example. And it's in our paper. So let's do a flip move on this guy. So there's the perfect matchings. There's the disk that I want to flip over. And what I see is that a G4, a bunch of G4s allow me to write it like this. So we're doing undirected because we'll just live it in the mod Z move category. And then you can see that just by doing virtual moves, I can move each of these things over. And I can move this over to the other side. So I can do all this in the virtual link category. or like a virtual move category. And what I get is the following. So that's about the extent that you can go. This, of course, is definitely not equal to this. And the reason why is because of the move that you would need to be able to go from here to here is the following. So this following is not a G move. So let's do this. So I always put things in quotes that are not true. If we were to translate this into virtual links, it would look like this. And you'll see why that it's clearly not. If you look at this carefully enough, you see that that's a virtual switch. So Lou called this a virtual switch. And it's exactly the type of thing. This is exactly the type of thing. Well, this is how he proved that there were virtual unlinks or unknots, or virtual knots that had the same Jones polynomial as the unknot, but were not the same as the unknot. I was using the virtual switch move. So there's no way to get from here to here by the usual G moves, by the usual, or translated into virtual links by the usual virtual link moves. And this is where we get at your question, right? Your question is, what are these things? And they are so think of the flip moves as special mutations. Now, there's all sorts of problems with mutations in virtual link theory and in just regular classical theory. It's, you know, you can't even, they're not even very, if you're looking at Khovanov homology with Z coefficients, with integral coefficients, you know that mutations, it's not invariant under mutations. So there's a problem already in defining Khovanov homology with integral coefficients. It's even worse for virtual links for the reason I described earlier, which is there's no ball. There's no, you can't take a virtual link and consider it to be in a three-dimensional ball of any kind, because you can only think of the virtual links as living in sigma G cross I, a thickened surface. So so the fact that basically what I had to prove that that the graphs were these virtual graphs, these graphenes are these not virtual graphs, not graphenes, but the trivalent graphs were invariant under flip moves, was to show that that while it's not true in general that Khovanov homology is invariant under mutations. If you allow for virtual links, if you allow for Z2 coefficients and you do a very specific type of mutation, then that thing is invariant. And so the way you should think about it is graphs, you should think of graphs, I'll end with this. You should think of graphs, trivalent graphs with perfect matchings, as sort of being invariant under mutations. And meanwhile, virtual links you know, and graphenes are invariants under things that are Reidemeister. So in my head, I have these two different pictures. When I want to do a graph invariant, I'm thinking of mutations. When I want to do a virtual link invariant, I'm doing Reidemeister moves. And it's helpful to see that they're different, and it's helpful to approach them from those points of view. But it's also exciting that when you're looking at a ribbon graph, trivalent ribbon graph with a perfect matching, you can almost in your head just think of them literally as virtual links. And that's another, so I'll end with this, right? Like everything here that I talked about is for a ribbon graph that's a regular three regular graph. In other words, it's a trivalent graph. But everything I've talked about today extends to, so the two-factor, for example, extends to conclude. Extends to K regular graphs. Whereas Jones polynomial definitely does not. So when you're talking about like the homology theories that I'm describing, they all can be, there's a really good chance that you can extend my homology theory to arbitrarily regular graphs where there was absolutely no correspondence whatsoever between Jones and Kauffman.
We have a conjecture that all graphs can be somehow represented in terms of.
Yeah, oh yeah, absolutely. You can.
Hence, we can try to do the same for trivalent.
You can always do this.
Sure.
Right.
Sure.
So you can always turn them into trivalent graphs. But what I'm saying is that there's a polynomial for the two-factor polynomial that looks, so to give you some idea, it's also described in Penrose. So you have a four-valent graph with a perfect matching, and then you can define the following polynomial. Oops. So all of this, the point being that the two-factor polynomial generalizes in ways that the virtual links don't. You know, the relationship between this K-map, there's no corresponding K-map between objects that look like this and knots. That's
well,
okay.
I would say, there is no corresponding map found yet.
Yet. Yeah, maybe that's right. Yeah, I'm totally willing to believe that. So, but it's interesting that, well, but my point is actually this lovely point that you have these two radically different ideas that come and share a common ground when you bring K down to 3. When K comes down to 3, then they literally become almost, they become friends, and they walk through the field together holding hands, and it's a beautiful and interesting relationship. Outside of that, you might be right, it might be really hard to get there. So that's where I would like to end today. So thank you so much. I appreciate your attention and your great questions.
So thank you so much. So please unmute your microphones and start writing on the chat line. I formulated quite a few questions on the chat line. So please, your questions, comments, remarks, and Scott, I would like you to answer the questions. well, if you want me to read them aloud, I can.
Question one, I'm just looking at them. You got to let me think. So question one, we have lots of singular crossings in various theories. Can you find any linking between them in
Oh, yeah,
order?
maybe it's quite apart. Maybe it's quite apart from your theory, but the idea is that so Denise Alyutka and myself set up a theory of non-existing chord diagrams, just in terms of adjacency matrices for chords, and actually many other crossings should behave like Reidemeister modes. They're crossing, so the question is how to define Z2 valued. I mean, Z2 valued crossings, Z2 valued, excuse me, linkings between chords. So if we do that, we will have well-defined maps not only to virtual knot theory, but also to some other theories. And for that theory, there is a Khovanov homology, for instance, which was set up by Igor Nikonov. Actually, there are many different combinatorial theories which may be related to each other. So there are some other questions, so please.
I
yeah,
just agree to that. And what I'm, you know, the core of this theory that I'm showing you today is actually, you know, this map right here, saying that they're really, you know, anything that you want to define in the graphene world automatically translates, and vice versa. So there are different questions, right? We're looking for link invariance if we're over here, but over here we're often looking for coloring invariance. So your question two is probably the question: how to define coloring and quandles as invariants of objects in algebraic geometry, complex surfaces, numerative algebraic geometry. So quandles are definitely can be defined over here, and fundamental groups and everything you want. My part of the reason why I'm excited about this, and I haven't talked about it much today, is that when you put, these are all ribbon graphs, and when you put a metric on the ribbon graphs, then there's this beautiful theory that goes to Grothendieck's child's drawings.
Oh, the son d'enfant, the son d'enfant.
The son d'enfant, and so there you can think of all these ribbon graphs that I've worked with today in front of you as being literally being representations of genus G surfaces with a specific complex structure on them, and then you can look at the Ajay space of those, and there's all sorts of beautiful mathematics that still needs to be done, and in reference.
Well, if you have a candidate for a speaker, we would be happy to invite him or her to one of our seminars. It would be great to have to talk about this on the phone.
Oh, yeah. Well, there's. I know. I don't know them personally, but I know their papers.
Great, great.
So question 3 for graphs, it seems that many. So yeah, in your back of your head, you should. In the back of your head, you should always be thinking of I'm still a topologist. I'm still a gauge theorist. So I love love thinking things about colors and graphs and all that. But there's I've got a bigger. I've got my problems that I'm trying to attack, and those tend to be topology problems. Another place where trivalent graphs with perfect matching show up are as the spines of surfaces in CP2 where the CP2 has been given the standard trisection. So there's you know, like it's related to the trisection theories now coming out.
Trisection, can you be more specific?
Trisection of four manifolds. If you take a four manifold, there exists trisections of them. There are ways of decomposing the four manifold that are Haggard theory. You know, like when you decompose a three manifold into a Haggard splitting or a Haggard decomposition. There's an equivalent theory for four manifolds, and they're called trisections. So you can and they have the same sorts of they were, you know, how do we say it? The trisections were designed to be in somewhat, you know, in a way that imitates Hager decompositions. So, but if you then embed a surface into a CP2 and ask, you know, what can I do with it? In the trisection, what comes out is a ribbon graph, and the ribbon graph has a perfect matching. So this is exactly how, you know, this is along the lines of what my student Peter Lambert-Cole did to prove the Thom conjecture without using gauge theory.
Which conjecture?
The Thom conjecture. The Thom conjecture says that the minimum genus of a surface of a homology class is given by a formula that it comes about exactly, you know, the minimizers for CP2, the minimizer surfaces in CP2 are always the complex lines. You always got to be careful because, but the two-dimensional complex Riemannian surfaces are the ones that minimize the genus.
Actually, there are there is a general principle saying that if we have some smaller theory and we want to minimize something, then we can do it from larger to smaller, and we can try to find projections or something like that. I mean, we have a projection from virtual to classical, and this proves quite a few theorems about genus, crossing number, or whatever. And we might try to think whether it may be related to projecting something to something having complex structure.
That's right. Again, complex structures play an important role here.
Yeah.
That's right. So you know, if you just thought that you just got a whole lecture on you know, like on graph theory, I would just ask you to maybe question that thought. You might have just had a whole lecture on topology, actually. So question 3. For graphs, it seems that many cycles, cocycles will persist if we consider the corresponding virtual knot as part of the pictures. So very non-planar pictures may replace variables. So this goes to your idea, right, of pictures. Is that what you're trying to ask, Silly?
Yeah.
Yeah. Yeah, no, there's you know, how do I say it? Right. So much of mathematics is, can we convert it into a picture of a graph, and, you know, where the graph contains all the valuable information. So, yeah, quite possibly. I don't know if I can answer that question, but it's certainly a good one to think about. And then problem 4, find the relationship between the Ulam theory that any n vertex graph can be uniquely determined by all of its n-1 subgraphs. In some sense, things, you know, this is trying to get at some of that, right? Because it's giving you a way of decomposing a higher valence graph into these cycles, into these immerse curves, and those immerse curves are actually telling you a lot about the actual graph. So maybe a question that I would take from here and change into is, given any caved regular graph, write down its hypercube of resolutions. So this is one where you have three coming in to a perfect matching, but you could do the exact same thing with 5 coming into a perfect matching, or 4, 7, or 10, or whatever. It would give you a big, huge hypercube of immersed circles, because each of these will split up into immersed circles. And does that determine the graph? So does the hypercube determine the graph completely? Okay, that would be an interesting question. Try to contact Olabas. Yeah, you talked about that. And then the strong embedding conjecture should be false. I don't know. I'm not so sure of that. But you know, it's still a conjecture, and it is the big conjecture.
Excuse me, Vasily, why do you think it should be false?
Well, I think there are too many degrees of freedom. 2 to the n is too many. So just send me a paper where it's concretely formulated. I think we have so many ways of mutations or other similar things which should. So let me concentrate on it. If you send me a paper, I will look at that more carefully. Paper with examples and motivations, I will look more carefully.
So, well, I'm not going to say that the conjecture is true. I'm not going to. There's no, for me, you know, it's like the Poincare conjecture, smooth Poincare conjecture. I would walk into my advisor was Ron Fincheshill. I'd walk into his office once a week and go, is the smooth Poincare conjecture true? And each week he'd say, yeah, I think it's true. And then the next week he'd come in, no, I think it's false.
By the way, are you familiar to Fincheshill-Stern invariants? I mean, formulas for Seiberg-Witten formulas?
Oh yeah.
Yeah, it would be great to see. Well, we have something for Alexandra polynomial, so it would be great to see whether we can do something with Jones.
Oh, this is. You know, how do I say this? When it comes, right, like to some degree, the Jones polynomial is still kind of a mystery as to what it means geometrically. In Cyber-Witten theory, it's a lot less. You know, we have much more kind of concrete grab on what it is. So being able to say, something works for Cyber-Witten, or something works in Cyber-Witten mode that you can translate it over.
We would be very happy to. Listen to Ron's talk. If he can contact him, on behalf of our seminar, so we would be extremely happy.
I'll tell you right now, Ron is retired, in the most, you know, in the most essential way. So I really doubt that I could convince him to come give a talk.
Oh, okay. Because, well, Scott Carter, for example, has retired, but he is very active.
I know. When I retire, I'm not giving it up. Like retirement means I get to do more math.
Who would you suggest, Scott, as a speaker about Seiberg-Witten invariants?
I don't know if Slavin's doing anything there. Tom Parker is really good at it. You might, yeah. Tom Parker would give a really nice talk on Cyber-Witten. Gromov, Tom Parker does Gromov-Witten, but Tom Parker's an amazing lecturer, very clear guy. So when he talks, you can understand what he's saying. One of the best teachers I've ever had. So yeah, we could reach out to Tom. And Ron Stern would also, I don't know if Ron Stern is retired like Ron Fincheshill was retired. So maybe Ron Stern.
Great.
For Ron's got grandchildren. He just wants to enjoy them. So.
Oh, what about Auckley?
Oh yeah, Auckley's really good too.
Yeah, Lou, if you can contact us by email, it would be great. So we have 3 seminars and many possibilities. Maybe this year something is going to finish, but next year we will have lots of possibilities, and we would be very happy to listen more about Seiberg-Witten.
Mm-hmm.
Yeah, good stuff. I love Seiberg-Witten.
Yeah, great.
The question 7. Oh, Lou actually answers question 7. Translating braids to graphenes is formally very similar to string category. It translates
Yeah.
almost, yeah.
Yeah. What I realized is that what Sophia and I did a long time ago, where we translated virtual braid group into, we actually translated it into graphenes, but it was before graphenes existed.
Probably.
So I should figure that out again. Yeah.
So, right. So the whole point with graphenes is that, you know, if this is a if that's a loop, right? If this is a braid, you can delete. So that would be R1. Here, let me make it look more like. So there's those. Once you start doing this, you see that you can easily start to put. You can easily start to think of graphenes as braids, and there's a nice. You can talk about the virtual braid group for graphenes, and it all translates nicely over. I'm trying to see what you're trying to say, Lou. Oh yeah.
Can you see what I'm holding up? What you're looking at here is a generator for the pure virtual braid group. And our idea was take the generators for the pure virtual braid group and make them into little, well, that's the graphene. That's a little stringy connection which we move around. So then what we actually did was translate the pure virtual braid group generators into the stringy category and then add the permutations and get the whole virtual braid group in a category over here. But it's really translating it into graphenes. I wasn't thinking of that. Graphenes didn't exist at the time.
So again, if you're, one of the things I hope that my talk is giving you is to give everybody in the audience a chance to think about is, I hope that it got you to say, oh, I want to go think about this some more. So, and the basic question, the basic thing is any question that you want to come up with about graphenes, probably open. So, there's plenty of neat new things to start thinking about with these objects, and talking about you can turn these things into braid representations and everything. Here, it's actually also pretty easy to actually see what the ribbon. You can actually compute the ribbon surfaces from these types of presentations pretty easily, and so you can get bounds on something I didn't even talk about, which is given a graphene, what's the minimum, given a graphene, it's got a matched diagram, that's a ribbon graph, it's got a surface associated to it, genus G surface. What's the minimum over all graphene over all matched diagrams is an invariant of the graphene. That in some sense, it's like the genus of a knot. And so that's by the way, that's also now an invariant of the original of the virtual link that it gets mapped to. So, which is also the classical invariant, right? Or if it's a classical knot, that's an invariant of a classical knot. So the question is, there's a whole wide category of what are bounds on the genus of the graphene. And there, I would say that the ribbon graphs or the braid representations are very useful. You can quickly calculate genus from a braid representation, where it's easier because you can see that you can kind of see the disks, what the disks are doing in that situation very easily. Oh, any other questions? Thank you for all these great questions. I really appreciate it.
Well, thank you so much. Colleagues, please unmute your microphones. Any further questions? I think we can share the records of this talk with those who could not, by one or another reason, attend it. So it was really a great talk.